Hi, I'm Dmitry,
Hey, I'm Chris.
and in this video we're gonna solve nice to a problem in the language called Sentient, which Chris wrote.
Indeed. So hopefully this is a bit more of an interesting example than the last one. This is a bit more involved, so we'll hopefully show more of the language. Okay, so maybe we should start by explaining what a knight's tour is. Basically in chess, a knight moves in a particular way. It can move basically in an L-shape pattern. And a knight's tour is a tour around a chessboard where the knight visits every square exactly once. So it can't go over its own path. Go on.
Oh, it's usually 8 by 8, right? That's chessboard.
Yeah.
But we're gonna do, like in this example in Wikipedia, smaller 5 by 5.
Yeah, we'll make that a parameter of our program so that if you want, you can solve more and more challenging versions of this problem.
Yeah.
Okay, shall we go over to
The editor.
an editor?
An editor.
Okay.
Yeah.
So I guess the first thing to think about when approaching a problem is about how are you going to represent things. And there are often lots of different ways to represent the same thing. I think the most intuitive way to represent a knight's tour is as an array of coordinates. So if we think of a chessboard as, in our case, like a 5 by 5 grid, maybe the bottom left is 0, 0 or 1, 1 or something, and then the top right is 5, 5, then a tour is really an array of those coordinates.
Yeah, so what you mean coordinates like 1, 2, 3, 4, 5, 4. Sorry, and that's the next.
I guess we should do 0 based,
Yeah, that's a bit more coding kind of.
I think.
So that's what you mean in knight is basically here. Then we keep coordinate jump here. I think that's correct. L shaped.
Yeah.
So something like that, and then we keep just coordinate. Right?
Yeah.
Of how we move.
I think so. I think that's the like if somebody gave me a knight's tour written down.
Yeah. It's
mean,
like in chess. You write down. They use different notation, but fundamentally it's just like you do it in chess.
Yeah. Okay.
Yeah. So and then we'll have it as then we use an array of moves.
Yes.
And it will be
so for a 5 by 5 board, I guess it would be 25 moves.
And this will be an array of. Here we have move type.
Yeah. So there are no type.
And it's going to be a tour, right? So it's going to be a knight's tour. What do we call this variable?
We can call it tour.
Okay.
Knight's tour.
Okay, I'll do it.
Yeah.
Knight's tour. Not gonna save on typing.
Yeah.
But there are no type addresses, so we have to do.
Yeah. So we'll represent a coordinate as just an array of 2 integers.
Yep. Something like that.
Yeah. And I think for this example, it makes sense to limit the cardinality of our integers. So normally integers, I made them quite small by default. They're only 8 bits.
So they're like bytes.
They're represented by a single byte. You can change that in the same way that you can with arrays. You can put 32 after there, or in fact 31 if you really want.
That's the best. Can you do 1 and then like a boolean?
Yes.
Does it work?
I don't see why it wouldn't.
Okay, let's not try it. But
I have never tried, but in our case, so integers are actually signed as well. Just for simplicity, I only implemented signed. So that means with if we want to go from 0 to 4, we need what would that be like? Probably 4 bits, 3 bits.
From 0 to 4.
Because it will go.
Oh, right.
If we use 4 bits, then it will go from -8 to 7. Because it's using 2's complement, so I think 4 bits is fine. If we used 3 bits, it would go from -4 to 3.
Well,
which is not quite enough to represent 0 to 4. So let's use 4 bits. That's fine.
Yeah.
It's just a little thing to be careful of sometimes, is making sure that you have enough bits to represent the thing you want to.
And then I guess we want to expose it, because that's the whole point.
Yes.
So I'll just run it, and that's a tour.
Yeah. A very interesting tour where we clearly visit the same cell more than once.
Yeah. Very nice. Well, cool.
Okay, so I think now we need to start thinking about constraining this tour so that it's actually a tour. So the first thing I think we should probably do is just make sure that our coordinates are actually in the range we expect them to be, because we don't want them to be like negative numbers, because that doesn't make any sense. So I think we should say we should go through all of the all the coordinates and check that they're all in bounds. So we can actually do that with the all function.
Yeah, because I guess right now we were just lucky that the 0 there could be minus 1000. We're constrained by int4, but they could be negative.
Yes, they could be negative at this stage. So we need to lock the range down even more. So here, Knight's tour is an array of coordinates. So let's call this argument coordinates. And then we need to get the x and the y values out of that. So we need x is the first.
And here, just to be clear what's going on, you just defined a variable called x, and in Sentient you can just type it, and Sentient knows what it is. You don't need to type because for Knight's tour we had to specify type, but for x we don't need to. Is it because it's not exposed?
It's more that there's in Sentient you can just assign stuff like you would in perhaps JavaScript or Ruby. You don't need to declare those integers first. The reason to do this is because we don't really have a value to assign to Knight's tour at this stage. We want it to be like this.
For Sentient to guess the value. That's why it needs to know what it is to be able to guess.
Yeah, you need to tell it the type.
Yeah, makes sense. Should be simple.
Yes, correct. Okay, so then we want to say that x is between 0 and 4, and y is between 0 and 4.
This is inclusive range.
It's inclusive, this between function.
And then it should be an invariant on line 11.
I guess so. Shall we just maybe try running that?
Yes.
If I can remember the keys. Okay, and it's not an exhaustive test, but let's just run this 10 times and see if any of those look invalid. And I think they're okay. We don't see any negative numbers there, and we don't see any 5s there, for example. So I think that's kind of doing what we want.
Yeah.
Okay. And I also think it's useful to do little bits of refactoring as we go, just to make the program more manageable. We haven't written our full program yet, and we're not really running tests or anything, so sometimes it's helpful just to give these things names. So I think we should perhaps define an inbounds function. Inbounds, which takes a number. Let's just call it n, and it just returns if n is between 0 and 4. And then in theory we can say x in bounds and y in bounds, and that should work the same. It doesn't work the same. You need a semicolon, yeah. Inbounds is not defined.
Yeah.
And then, so this is, I think I mentioned in the previous video, there's a little trick, but we never actually explained what that trick was. What I tend to do, because there's this requirement that you must define a function before you use it.
Right now what it says, I don't know what inbounds is because it's defined afterwards, right?
Yes.
So that's the problem.
Exactly. So what I will usually do is put all this stuff in like a main function, which doesn't have any special meaning as it might do in other languages. I'm using...
I can do... Okay. Could do it a bit more efficiently.
I'm not much of an IntelliJ user. So then by having that main function, it means all of the functions are defined. Let's move that expose up into there as well. And then we can call that right at the end of the program, just once we know everything's defined. And then let's try that again. X must be declared.
Right. That's because it should be M.
Okay.
Now this
Okay.
is the same.
So it looks the same.
Exactly
Our refactor
the
is
same.
kind of complete. And then I want to take it even further, if I may. And
But just to ask, but in general, Sentient is deterministic. The results it prints out, they're seeded by, it uses the same seed. So we could actually, if we genuinely just refactor, it should give us the same output.
it should
We could like do approval testing, basically.
Yeah, it depends slightly on the backend that's used. In theory, they could be
But you could
non-deterministic.
lock it down, I guess.
Yeah. So I want to make use of this feature that you can, like, it's very lightweight to do method extraction in Sentient. So I'm going to define a function, which we can just call x, which takes a coordinate, and it just returns the first, so we'll say coordinate 0.
Yeah, that looks cool to me.
And then we'll do the same with y. And then this just becomes coordinate x is in bounds and coordinate y is in bounds.
Yeah. And the way it also works is because coordinate is the first argument to this function, then we can pretend that this function is part of coordinate, and you can emit parents or something like that. So you don't have to type empty parents. That's why it even looks like a property or something.
Yes, yeah, and that's a very Ruby type thing.
Yeah, but just in case.
Yeah.
Somebody question that.
I'm sure they will. Okay, let's see again if that still works, because we've made a few more changes. And
it looks identical.
Okay. All right. So maybe we could even, I'm tempted to actually make this also take a coordinate. It feels like that's our atomic unit.
Yeah, actually that's good. Yeah, I didn't think.
And then
I like the idea. We can just copy this basically into that.
Yeah. So then I guess we need to call between on each of these.
Yeah, that's fine. I'm happy with that.
Okay, all good. And then up here,
should we change this to inbounds, coordinates inbounds, without
it? Yeah, so we can do that. And actually,
so that's like one step. That's one
step of refactoring.
Yeah.
So let's check that. Yeah, I'm always wanting to rush ahead.
No, it's cool. It's for my understanding.
And then the next thing we can do, this is kind of like a useless function here, because it's taking a coordinate and then it's passing it through to this inbounds function as an argument. So really what we want to do is just call inbounds on each of the coordinates in the Knight's Tour.
Yeah.
And In JavaScript, you might do that by just saying inbounds and pass that as like a function.
Reference to a function, what a pointer.
Sentient has the same idea. You just use a little star there in front of it, and then it points to that function. And in theory, that should, I keep pressing the wrong thing. That should still work.
Yeah, so it's equivalent. Oh, that's cool.
And I like this pattern because now our main function is pretty clean. We define our tour, and then we check that all of the coordinates in that tour are inbounds. And that feels like, as a human, I want to express the rules of this problem. I feel like we've done an adequate job of doing that. So now on to the next step, which is, I guess,
moves are reasonable, or what's the next
step? Maybe that should be the name of our function. So we need to say if I'm the knight and I'm in this cell, this square on the chessboard.
You mean, for example, this cell?
Yeah.
And then if the next step is this in the tour, this must be a valid move. So the second step cannot be here.
Yeah.
So this is an invalid move, and this is a valid move.
Yeah, we need a way of saying, going from each like consecutive step that it's following an L-shaped pattern. For this, we need like one of the array iteration.
So it's just going to be some invariant, right? So that's definitely something. I don't know what.
Yeah.
And then we'll do nice tour because that's what we do. That's also cannot be wrong.
Yeah, the only thing we have available right now.
And then it's some function. Is it like what? Each cons or something like that?
Yeah, so maybe we should flick over to the Sentient standard library. So if you scroll down, standard library. Array. So arrays have different ways of iterating through them. You can just do an each, but if you scroll down, there's one called each cons, which stands for each consecutive.
I think the main one is this. It has lots of good documentation. Then there is each combination. Really, that's advanced.
Yeah,
and then there is each cons.
Yeah. So each cons 1, 2, 3, 4 will go 1, 2, then 2, 3, then 3, 4. So it's like going.
It's a sliding window of 2, basically.
Exactly.
With step 1.
With step 1. Yeah. Maybe that's a better generalization. We should add to the
I thought there was something like. Yeah. Cool. I can go back. And so if I do each cons, and that's going to be cons, or what should I call it?
So
function. Sorry.
I think we do actually say how big our sliding window is as the first argument. So we need a 2.
Right. So it's already like a sliding window.
I think so.
Cool. And that should be, what should I call it?
Pair. Yeah. Sounds good. So
then inside here do pair.
So
0, that's the first one, and then it should be should be valid move, is valid move, I think. Maybe I'm just thinking very abstractly.
Yeah.
These are 2 moves, it must be valid. And maybe it's not this invariant, but this
you
is
put it inside, And I'd probably add a question mark to the method name because it's
that's
convention
in Sentient.
I guess so.
I was
going to say Ruby, but it's also
it's
in
Sentient now. Okay, so now we need this function is valid.
Yeah.
Question mark. And is that coordinate 1 and 2?
Yeah.
That's basically what it is.
Sure.
And so it will need to return. I just keep typing. It will return.
It's good. It will return.
And there are
a
few ways which are valid moves, right? Like this L-shape rotated around.
Yeah. So the way we could do this is we could get the x coordinate of coordinate 1 and coordinate 2 and subtract one from the other.
Okay. So we're doing x coordinate 1. Do x coordinate of 2, and
so that gives us like the difference between them.
So in this example, it will be that's invalid. But if we move x, it will be from, well, that's not correct, right? This should
be 0, yeah.
0 based.
Yeah. Is this our x coordinate along the top?
Yeah, that's what I do.
So that first one is at 0, 1.
And then this goes to 3, basically. So the difference...
I think, isn't that
2... It goes to 2, yeah. So that's 2 minus 0 is fine. But if we shift both, it will be 3 minus 1 to have a bit more interesting example. And that should equal to 2. Except that it can also be the other way around.
Yeah.
Right? So it should be abs or something like that.
Yeah, exactly. We should...
Can I do
if it's negative, we get
abs?
the absolute. You can do that.
Also in the library.
Yeah.
And that's... what is this?
The x delta, I'd probably call that.
Okay. So x delta equals to, and something else, y delta. If we do this, then there will be definitely y delta.
Yeah.
I'm pretty sure. Y. And y delta equals 1 in this case. And there must be like the reverse. Like
the symmetrical case where
it's very hand-wavy.
X delta is 1 and y delta is 2.
Okay.
You could probably also, if you wanted, like put them in an array and I don't know, sort the array and check it's equal to 1, 2 or something. But
I think just these two.
that's okay.
I'm really happy with this. So should we run this?
Yes.
I think it's ready. Ooh, this looks more interesting.
It does look more interesting.
It's a bit difficult to know.
So the first thing I notice is that it's gone from 3,2 to 4,4, but then it's gone back to 3,2.
Yeah, that's...
And one of the rules of the problem is you can't visit the same square.
You're probably doing one rule at a time, so it's your turn.
But it's good. We're like, the thing I like about working in this environment is you can layer up your constraints one by one. So you can kind of build up to a more and more sophisticated thing. If you're writing a search algorithm from scratch, you might have to like really think hard about all the constraints up front and figure out like how to cope with that.
In a way, I think there is a very interesting analogy with property-based testing, because like you could drive your actual implementation through properties, but you have to write both implementation and properties. Here you just write properties, and Sentient does the rest for you.
It tries to. I mean, it's probably worth the disclaimer is that sometimes you'll write one of these programs and Sentient will just hang on it for forever. Like if your program doesn't have any solutions, Sentient might after some time be able to say there are no solutions. The way it indicates that is with like an empty output.
Yeah.
But sometimes it might just run for weeks and weeks and won't tell you.
Well, but do you think it would be different if you were implementing manual? You'd
have the same problem.
Yeah. So
it's just it's not made of magic. It has like something real behind it.
Yeah. So.
So we need to add a constraint that all of the coordinates are unique. Yeah. And that's actually one of the things I spent a bit of time building into the language because it's quite hard to write yourself. But you can now just say Knight's Tour dot unique.
Oh wow.
And
okay.
It does like a pairwise comparison of every element against every other
in some
element.
efficient way, I suppose.
Yeah, I think it does like n squared over 2 comparisons, which I think there is a more efficient way to do it if you know that the array is sorted, but in general, you don't. Anyway.
As efficient as it can be for random arrays, basically.
Yeah, let's see what happens. So here it might take longer, but it seems like it's giving us a few solutions. Can we maybe stop it and verify one of them?
Just like eyeball them and map them here somehow. What do you think?
Sure.
If I do 2, 0, 4, 1, that's 2, 0 is here, so I'll delete those. We just do so 2, 0. Then 4, 1, yes.
Maybe we could use letters of the alphabet as
good idea. Maybe then 3, 3. which is just here. Yeah,
That seems valid. Yeah.
Then 1, 4. Yeah, why not? What's next? D. 0, 2. Yeah. Do we go the whole way? All the way to 1, 0?
I'm sure if it's worked for the first 5, it must surely work for the rest, right?
Right. Okay. Yeah.
I don't think mathematicians would be very happy with that conclusion, but it's ended at 0, 0. I can't see any duplication in there. There is one nice feature as well that I just wanted to mention, which is you can actually assign. So this program is considered like. It's easy to change the program. You could add more invariants in and so forth, but you can also do a little bit of that on the command line. So if I wanted to say, I want a tour that starts in a specific place.
Oh, you can add additional constraints.
So I could say, assign Knight's tour, and then this just takes some nested, because it's an array, we can now say at the 0th element, at the 0th.
Oh, wow.
So 0th row, 0th column, assign that to 0 or something. And then, so it's made it so that this always starts at 0. Or if you wanted to also limit this, you could, for example, I think say the entire coordinate is that. Maybe.
Yeah. That's cool.
So let's say it like starts in the middle, which would be 2, 2, 2.
If there is one. Oh,
if there is one.
Nice. Yeah. Yeah, that's cool.
So yeah, that's just some of the things you can do. There are more options. Like there's a way to compile these programs, but then run them later if you want. And there's an optimizer and a few of the bells and
just doing a bit of cleanup. But I think it's like really niche programming. Like these things, this is just trivial, right? And then the actual night tour is pretty much in like 15 lines of code.
Yeah.
It's like whenever I tried to implement it myself in normal language, it was way harder than this.
Yeah, you have to do like a backtracking algorithm or something.
It also just always feels so custom, and there is like accidental complexity, I guess that's what I mean. It feels like so much accidental complexity, and here it's just pretty much there. It feels like more essence of the problem than just random things.
I think as well that it's nice to be able, as I said before, to be able to layer these constraints up, because the advantage is you can really work towards a solution step by step. It's like little tiny baby steps, which really fits my style of programming, where I'm like very gradually building up complexity, usually with a test suite and bits of refactoring and so on. And I don't have to like do all that thinking up front. So yeah.
That's cool. I guess I'm gonna stop here.
Yep. All right. Cool.
Yeah, cool. Thank you.
Thanks for having me again.
Yeah. Thanks for watching.